about object-oriented programming, or OOP, in Java. Look, if you've ever felt completely overwhelmed staring at massive walls of code, this is absolutely the solution. At its core, OOP is all about a massive shift in perspective. Instead of organizing our software around functions, which, are really just sequential lists of actions, we organize it around objects. An object is this neat, self-contained unit that holds both its data, we call those fields, and its behaviors, which we call methods. It's just a beautifully intuitive way to structure your code.
Now think about this. What if you could build software the exact same way you build a car? You don't build a car by pouring molten metal into one giant car-shaped mold. No way. You assemble it from distinct, highly functional parts. You've got an engine, wheels, doors, and each part has its own specific data, like its size or tire pressure, and its own specific behavior, like accelerating or opening. Well, that right there is the magic of OOP. It bridges the gap between highly abstract code and real-world physical design. It just makes your programs infinitely easier to build, manage, and understand.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with blueprints and living objects, then move to creating and initializing objects. After that, we hit the 4 pillars of OOP, run through some essential Java keywords, and finally bring it all together with the real-world car system. All right, kicking things off with Section 1, Blueprints and Living Objects. So, everything in object-oriented programming starts with a fundamental division. It's the split between the concept, the pure idea of a thing, and the actual physical reality of that thing. It all starts with a class. A class is literally just a blueprint. It's a template for creating objects. Think of it like a paper schematic. If we sit down and write a class called student, we're essentially defining that every student in our entire system should have certain properties, maybe an integer variable for their roll number and a string variable for their name. We also define their behaviors, like maybe a display method to print out all their info. But, and this is a really critical point, this class is just a static template. It is not an actual living, breathing entity yet. It's strictly the design. Now, what's really interesting about this is how memory allocation works. An object is an actual, concrete instance of a class. When you just have that student class blueprint sitting there, your computer isn't actually using up any memory to store a student. Memory is allocated only when the object is explicitly created. That's the exact moment the blueprint comes to life. So we take our student class, allocate the memory, and boom, we create a specific living instance, like a student whose roll number is 101 and whose name is Rahul.
Moving right along to Section 2. Creating and initializing objects.
Okay, so how do we actually bridge that gap? How do we use our code to breathe life into those static templates? Well, Java gives us this beautiful, highly predictable procedural flow for creating objects. First, you have the class. Second, the object gets created using the specific new keyword. And the second you type new student, step 3 triggers. The constructor executes. Fourth, memory is finally allocated in the system. And fifth, with all of that done, your object is alive and you can finally call its methods. That new keyword, that is literally the spark of life for your object. Let's zoom in on step 3 for a second, the constructor. A constructor initializes an object automatically the exact moment it's created. And you essentially have 2 main options here. You can use a default constructor, which takes 0 arguments. It's basically handing you a completely blank slate. Maybe it just prints out object created and that's it. Or you can use a parametrized constructor. This one is great because instead of a blank slate, it lets you set very specific properties right out of the gate. You pass in parameters, so the object instantly knows its ID is 101 and its name is Amit, the absolute second it's born.
Right, so once your object is alive and initialized, you want it to actually do stuff, and that is exactly where methods come in. A method performs a specific task. For example, if you create a calculator class, you'd probably define an add method. This method takes very specific inputs, let's say 2 integers, a and b, and it returns their sum. So you create your calculator object using new, and then you call that add method, pass it the numbers 10 and 20, and it reliably spits out 30. It's a highly specific, repeatable behavior bundled directly into the object.
Which brings us to Section 3, the 4 pillars of OOP.
Now that we know how to create living objects, we need to give them complex dynamic behaviors and relationships. The absolute foundational rules of object-oriented programming live right here in these pillars. The first pillar is encapsulation. This means wrapping your data and your methods tightly together in one single unit and, crucially, protecting that data using private variables. So the crucial point is that encapsulation gives you serious data security and controlled access. Imagine you have an employee class. You absolutely do not want anyone to be able to randomly change an employee's salary from anywhere in the program. So you make the salary variable private. The outside world literally cannot touch it. Instead, they have to go through a public method you explicitly provide, like setSalary. The actual data is hidden safely behind that method, which gives you ultimate control.
The second pillar is inheritance. This lets one class acquire the properties and methods of another completely different class, which is just incredible for reusing your code. You can have single inheritance, where a dog class extends an animal class, meaning it inherits its basic ability to make a sound. You can have multi-level inheritance, stepping down from animal to dog to puppy. Or hierarchical, where maybe both dog and cat extend outward from the exact same animal base class. Now, quick aside, Java actually has a quirk here. It doesn't support multiple inheritance directly with classes, just to avoid confusion if two parents have the same method, but it does support it using interfaces, which we'll get to in a minute.
Moving on to the third pillar, polymorphism. The word basically translates to one interface, many forms, and this brilliantly illustrates just how flexible Java can be. We've got two flavors of this. First up is compile-time polymorphism, which we achieve through method overloading. This is where you use the exact same method name, like add, but you give it different parameters. Maybe one version adds 2 numbers, while another adds 3. The compiler just figures out which one to use based on what you hand it. Then we have runtime polymorphism, achieved through method overriding. This is when a child class, like dog, provides its own exact hyper-specific implementation of a parent's method, so overriding the animal's generic sound method to specifically print out dog barks instead.
And the fourth and final pillar is abstraction. Abstraction is all about hiding the messy, complex implementation details and showing only the essential features to the user. We do this using abstract classes or interfaces. Think of an abstract class called shape. It might declare an abstract method called draw. The concept of drawing exists in the abstract, sure, but the shape class itself has absolutely no idea how to actually draw a shape. It's only when we create a specific child class, like circle, that we actually write the code to draw the circle. We hide the how from the overall system, which keeps our code super clean and modular. All right, shifting gears to Section 4, Essential Java Keywords.
To actually implement all those pillars we just talked about, we have to look at the granular tools, the modifiers, and the syntax rules that act as the glue and the guardrails of our Java code. Let's talk access modifiers. These control visibility. Private is the ultimate lockdown. It's only accessible within the exact same class. Default opens things up a bit, allowing access within the same package. Public is a total free-for-all, accessible from literally anywhere. But protected? That one is unique. It's accessible in the same class, the same package, and any subclass, but it can only cross into a totally different package if it happens through inheritance. It's a very specific security clearance.
Next up, we have our identity keywords, this and super. The this keyword refers directly to the current object you're working in. So if an object has its own internal ID variable, but it just received a brand new parameter that's also named ID, you use this.id to tell Java, hey, I mean the ID belonging to this specific living object right here. On the flip side, super refers to the parent class. So if our dog class is being initialized, it can actually call super to trigger the parent animal constructor first. It's essentially how Java manages internal identity and keeps track of who's who in those inheritance family trees. Then we have static and final. When you declare a member as static, it belongs to the class itself, rather than any individual created object. For instance, if every single student in your program goes to ABC College, you'd make that college string static. It becomes a shared concept across all students, which saves a ton of memory. The final keyword, on the other hand, acts like a deadbolt. It completely prevents modification. If you set a final integer called age to 25, that value is permanently locked down. It literally cannot be changed by any other part of the program, ever. Finally, looking at the structural side of things, we have packages and interfaces. Packages are pretty straightforward. They simply organize related classes together. It's exactly like keeping your computer files in specific folders. It keeps your workspace tidy and prevents annoying naming clashes. Interfaces, which we touched on a bit earlier, contain method declarations but without the actual code bodies. When a class implements an interface, it is essentially signing a strict behavioral contract.
It is promising the system I will write the actual code for these exact methods.
Let's move to our final segment. Section 5, the real-world car system.
Okay, let's take every single concept we just learned and see how it builds into a complete real-world architecture. Because this maps so perfectly to physical reality. Our blueprint, our base class, is simply car. From that blueprint, we spin up distinct living objects, a BMW, an Audi, a Tesla. We use encapsulation to make all the dangerous, complex engine variables completely private, protecting them from outside interference. We use inheritance so that a brand new class, like electric car, automatically extends and acquires all the base features of the generic car. We see polymorphism in action because, hey, while all cars have a start method, a gas-powered BMW implements that start method very differently than a battery-powered Tesla. And finally, abstraction. As a driver, you just press the start button. You don't need to know the internal engine logic at all. The interface is dead simple, while all the heavy complexity is completely hidden away.
And honestly, that physical, intuitive architecture is the true power of OOP in Java. It is entirely about bringing the logic and structure of the real world straight into your code. Abstraction lets you press start without ever needing to know the engine logic. So I'll leave you with this final thought as we wrap up. As you sit down to start designing your own software, what complex systems will your objects hide today? Thanks so much for joining me.